Hello students, welcome to Set Theory class 2. In our previous class, we have learned what is set, intersection, union, complementation of a set, etc. etc. Today, we will learn more algebraic operations on a set. Okay? First of all, I am defining difference of sets. Okay, what is difference of sets? At first, we have to take a universal set. Let U be a universal set. Okay, let A and B be subsets of U. Okay, now we are defining difference of A and B, and it is denoted by A minus B. Okay, and this equals to x such that x belongs to A but x does not belongs to B. Okay, so what is the picture of this definition? See, this is our universal set. Okay, U, in which A and B are situated. Suppose this is our A set and this is our B set, A and B. This is called Venn diagram. Okay, now the common portion of AB is this. Okay, this is A intersection B. Now we have to find those elements who are only in A but not in B. Okay, so this type of elements are situated in this region, in this shaded region. Okay, in this shaded region. So in this region, only the elements of A which are not belonging to B are situated. Okay, that means these elements are only in A but not in B. Okay, so this is our picture of our definition. Fine, so this is our difference of two sets. Okay, now I am defining the symmetric difference of two sets. Symmetric difference of two sets. This is our A minus B, only this region. Okay, so symmetric difference of two sets. Again, I am taking the subset A and B of the universal set A. Okay, so symmetric difference of A and B is denoted by A delta B. Okay, this is our symmetric difference, and this is equal to A minus B union B minus A. Okay, if I draw the picture of this definition, so this is our universal set, this is our U, this is our A, this is our B. So A minus B is the shaded region, okay, and B minus A, similarly B minus A is the shaded region, this shaded region. Okay, now see, observe that we are eliminating the intersection part from this diagram. Okay, so the symmetric difference of two sets A and B is defined by A minus B, that means this shaded region, union B minus A, that means this shaded region. Okay, now I will write some properties of union and intersection. Okay, properties of union and intersections. Okay, notice, fine. At first, observe that okay, let U be our universal set. Okay, universal set, and A, B, C subset of U. Okay. So if we take A with union phi, okay, if we take A union phi, then this gives us A, because phi is subset of any set. Okay, so if we union phi with a non-empty set A, then see this picture, this is our A. Okay, this is our A. So if we, phi is subset of A, so if we take union phi with A, then obviously it will give A. Now if we take intersection in between A and phi, then I have to take the common parts of phi and A, so it will give us phi, because phi is subset of A, okay, and phi is subset of phi, so the common part of A and phi is nothing but phi. Okay, okay, now if we take union in between A and the universal set U. This is union sign and this is universal set. So this will give U because see, the A set is your room in your house and U set is your house. If you take union of your room and your house, then you will get the house. Okay, so similar concepts is here. And if you take intersection in between A and U, then it gives A, because if you take the common part of your room and of your house, then it will give you room. Okay, now see, this property has a name, and the name is idempotent. Idempotent property. Okay, this property tells us that if you union A with A, then it gives A. Why? And if you take intersection with A, this gives also A. Why? Ask yourself. Okay, you are able to find this answer. Okay, now D. This property name is absorptive property. Absorptive property. This property tells us if you take union in between A and A intersection B, then this will give A. Why? See, if you draw the Venn diagram, this is our U. Okay, this is our A, this is our B. Fine, this is our A intersection B. Okay, now if we take the union in between A and A intersection B, then we will get this part along with this part. Okay, so there is no B's element. So this is very much clear from this picture that A union of A intersection B is equal to A, and similarly if you take this, then you will get B. Okay, and if you take intersection between A and A union B, okay, then these also give A. Why? Ask yourself. Okay, so from this and this, we can say A intersection B is subset of A. Okay, and A is subset of A union B. Okay. Now commutativity. Okay. A union B is equal to B union A, and A intersection B is equal to B intersection A. Okay. Now associativity. Associativity property tells us that if you take union in between A and B union C, then only we have to shift this bracket and we will get the same union. Okay, and similar result will hold for intersection. Now the last property is distributive property. Distributive property. Okay, this property tells us if we take union in between A and B intersection C, then it will give A union B intersection A union C. Okay, and A intersection B union C gives us A union C, A intersection C union A, this is a union. Okay, this is union A intersection B. Okay, see, the properties 1, 2 and 3 are very much clear from the Venn diagrams, but the property number 4, which is distributive property, this has to be proved. Okay, so now I am going to prove this property. Okay, and also you will learn how to prove two sets are equal. Proof of property 4. See, we have to prove that A union of B intersection C is equal to A union B intersection A union C. Okay, so we have to show these two sets are actually equal. So at first we have to take an element x from this set. Let x belong to A union B intersection C. Okay, this implies that X belongs to A, or I am using only the definition of union, okay, or X belongs to B intersection C. Okay, this implies X belongs to A or X belongs to B. Now we have to use the definition of intersection, and X belongs to C. Okay, now okay, I am giving here the brackets. Now this implies X belongs to A. Okay, X belongs to A. Okay, look at this line. X belongs to A or X belongs to B and X belongs to C. This line implies that X belongs to A or X belongs to B. Okay, and X belongs to A or X belongs to C. See, this line and this line are looking different, but the meanings are same. Okay, so this implies that X belongs to A, X belongs to A union B. Okay, and X belongs to A union C, because we are now using the definition of union, and this implies that X belongs to A union B intersection A union C. So this shows that X belongs to A union B intersection C implies X belongs to A union B intersection this. So this implies A union B intersection C is subset of this set. Okay, now let y belongs to, now see, we have shown that this set is subset of this set. Now we have to show that this set is subset of this set. Okay, then the equality of two sets will hold. Okay, let y belongs to A union B intersection A union C. Now this implies that y belongs to A union B and y belongs to A union C. Now this implies, just I am using the definition of union, y belongs to A or y belongs to B. Okay, and y belongs to A or y belongs to C. Okay, fine. Now this implies that, see, y belongs to A, y belongs to A. So just y belongs to A or y belongs to B, and y belongs to A or y belongs to C. So this line implies that y belongs to A, the y belongs to part is common. Okay, or y belongs to B y belongs to B and y belongs to C, because in this part y belongs to A or y belongs to B. So either y in A or B, and this part either y in A or B. So both so from both the part y belongs to A, but this statement y belongs to B and y belongs to C, this implies that or y belongs to B and y belongs to C. Okay, now this implies that y belongs to A union B intersection C. So this implies that A union B intersection is subset of A union B intersection C. Okay, now I am naming this 1 and 2. Now I am writing here from, so this is subset of this and this is subset of this. So from 1 and 2, from 1 to we have A union B intersection C is equal to A union B intersection A union C. Proved. Okay. Now we will see a very important property of complementation. Okay, that is De Morgan's law. De Morgan's law. Okay, this is very important property of complementation. This law tells us that A union B, its complement is equal to A complement intersection B complement. Okay, and complement of A intersection B is equal to A complement union B complement. Okay, now I will prove this, and the proof of this is similar to this. So this is 1 and this is 2. So proof of 1. Let X belongs to A union B complement. Okay, now this means that X does not belongs to X does not belong to A union B. So this implies X does not belong to A union B, right? See, when we take union of two sets, then actually we are gathering the points in A and B. Okay, but in this case X does not belong to A union B. It means neither X belongs to A, not X belongs to B. Okay, so this implies that X does not belong to A and X does not belong to B, because if X belongs to one of A and B, then X belongs to A union B. But here X does not belong to A union B, that means X does not belong to A and X does not belong to B. Okay, this implies that X belongs to A complement. Okay, because this is A, so if X does not belong to A, then X belongs to X minus A, and that is a complement. Okay, and similarly X belongs to B complement. This implies X belongs to this. Okay, now so from these steps we have this subset of this. Okay, now let Y belong to A complement intersection B complement. Now this implies Y belongs to A complement and Y belongs to B complement. Now this implies Y does not belong to A and Y does not belong to B. So this means that Y does not belong to A union B. Okay, so this implies Y belongs to A union B complement. Now these steps imply okay, so from 1 and 2, from 1 and 2 is equal to this. Okay, now you have to try to prove this. Okay, now I am defining set of sets. Okay, see, we have defined a set as a collection of its elements. Okay, its elements. Now if the elements be sets themselves, then we have a family of sets. Okay, see, suppose I have a set 1 2 3. Okay, now the subsets of S are, I am writing here, the subsets of S are obviously 5. Okay, S is subset of itself, so S, and this type of set is called singleton set. Okay, because there is only one element. The set is containing only one element. Okay, this. Okay, now this is a subset, this is a subset, this is a subset of set S. Okay, this is a subset of S, this is another subset of S, and this is the last subset of S. Now, considering these sets as elements, okay, and constructing a new set where where these sets are elements. Okay, so phi is okay, we are creating a new type of sets. We are creating a new type of set of sets. Okay, and if we collect all of the subsets of S, and then we are making a set T, then this set is called power set of S, and this is denoted by P of S, the power set of S. Okay, so what is power set of S? Power set of S is equal to collection of all subsets of S. It means we are creating a new set in which the elements are nothing but the subsets of S. Okay, and if see, there is a concept of finite set and infinite set. Okay, if S is a set containing n elements, where n is a natural number, then where n is a natural number, then S is called finite set. Okay, finite set. Otherwise S is infinite. Okay, the infinite set is not in our discussion. So if S is finite and containing n elements, okay, then we are defining cardinality of S and denoted by is equal to n. Okay, and the cardinality of PS, that means power set of S, is equal to 2 to the power n. Okay, so this is all about our set theory. In the next class we will learn relation. Okay, so I am stopping my class here.